Welcome back, signals and systems enthusiasts. Can I say that yet? Well, we are, if you look behind me here, 8.1, 8.x. So we are at a new topic, right? And we spent a long time on 7.x, which was the continuous time Fourier transform. So now we're talking about the discrete time Fourier transform. And we are not going to cover this in as much detail as we did the CTFT. That's because a lot of the details are the same. And I don't want you to get the impression that the DTFT is just not as important. One could argue that being in the digital era that we live in, the DTFT could actually be more important. You could certainly argue that. So I view these things as being equally important, the DTFT and the CTFT, but we're not going to cover the same details. Instead, we're going to focus our time on the subtleties that make DTFT a little bit different than CTFT. So let us start our journey through the DTFT. And we'll start by reminding ourselves of how we calculated the Fourier transform in continuous time. We took our signal, x of t, multiplied it by e to the minus j omega t, and then integrated over time, minus infinity to infinity. That was the analysis equation, or the Fourier transform. And then given the Fourier transform, we said that there is an inverse Fourier transform, which we are calling the synthesis equation, where you take that Fourier transform, multiply it by e to the j omega t, integrate it over omega from minus infinity to infinity, and divide by 2 pi, and that gives you x of t. Now, I derived these two things for you, and I will not do that for discrete time. We'll just kind of make a jump knowing what we know about the discrete time and how it's different from continuous time. So how is discrete time different from continuous time? Let's remind ourselves, and I'm going to write it out because it's so important. Frequencies differing by 2 pi, or multiples of, are identical. Okay, let's remember why that is. If I take a basic, i.e. single frequency signal, e to the j omega 0 n, the claim is that it is equal, so I'll put a question mark there because it's a claim, to a frequency that is omega 0 plus some multiple of 2 pi. So k is an integer, so we have a multiple of 2 pi. So the frequencies are differing by a multiple of 2 pi. And so on the right, I can use properties of exponents to write this as e to the j omega 0 n times e to the j 2 pi kn. So k and n are integers, and so k times n is an integer. So I have an angle, think about the complex plane, of a multiple of 2 pi. So I just go around the circle, multiples of 2 pi, and then I end up at the coordinate 1, 0, meaning 1 real part, 0 imaginary part, i.e. 1. So this, in fact, does give me back the original signal. So we have to keep that in mind. So how does that change? The Fourier analysis of a discrete time signal? Because remember, the Fourier analysis is telling us the frequency content of the signal. Well, for one, the synthesis equation is going to become this: 1 over 2 pi times an integral, and it's still an integral because the Fourier transform, the discrete time Fourier transform, is still a continuous function in omega. So it's still an integral, but we're only going to integrate over a range of 2 pi, because if we integrate this thing more than over a range of 2 pi, then we start double counting frequencies or triple counting frequencies. So we only need to integrate from the entire spectrum, but in discrete time the entire spectrum is over 2 pi. And then we're actually going to use the notation e to the j omega, because e to the j omega is periodic with period 2 pi. And so this is going to be our notation to signify that this is different. This is the discrete time Fourier transform, and this is the continuous time. So you can think of e to the j omega as kind of peanut butter and jelly and bread, right? Omega really is the variable, if that's the peanut butter, or whatever your favorite ingredient there is. Then j is the jelly and e is the bread. Those three things come together all the time in discrete time Fourier transforms. And then we're going to take e to the j omega t d omega. So this, not t, excuse me. E to the j omega n d omega. And this now becomes our synthesis equation, or alternatively you could say this is our inverse Fourier transform. You give me the Fourier transform of our signal, and this is how I reconstruct x of n. So now how do we get that Fourier transform? So x of e to the j omega is equal to, well, this won't be a surprise to you, x of t becomes x of n. Okay, and an integral over t becomes a sum over n, and we're going to go from minus infinity to infinity, and then we have e to the minus j omega n, like this. So this is straightforward, I would say, given the continuous analog, right? And so this is the Fourier transform equation, and or more specifically the discrete time Fourier transform, or you could call this the analysis equation. And then this is the synthesis equation, or you could call that the inverse Fourier transform. Okay, so we already talked about a big difference here. This is one of the differences, right, in calculating the DTFT, and it has to happen now. Here's another big difference related to this. If you're going to calculate a discrete time Fourier transform, this thing, and if the discrete time Fourier transform is supposed to tell you the frequency content of the signal, then the discrete time Fourier transform must be periodic with period 2 pi. With period 2 pi. Now it can repeat pi, because anything that repeats pi also repeats 2 pi. But it has to repeat every 2 pi because this thing tells you the frequency content. So for example, if you had a lot of energy, I'm just speaking loosely here, but a lot, right, of energy, who knows what a lot means at this point, but we'll look at examples later. A lot of energy at omega is equal to 0, right? That's the DC frequency. Then, x of j omega 0, is large, is what we would say, right? Well, that must mean you have a lot. So this would imply then you have a lot of energy at omega is equal to 2 pi because of this reason here, right? Frequencies differing by multiples of 2 pi are identical. So these differ by 2 pi, or 4 pi, or minus 2 pi, or minus 4 pi. These are also considered DC frequencies. We saw something similar when we were talking about Fourier series. So that must mean then, for everything to be consistent, x of e to the j 2 pi is large, right? And x e to the j 4 pi is large, and so on. And so to summarize, this must be true. It has to be that way. So this is a huge difference then. And it turns out then, if you this is a huge difference for discrete time Fourier transform versus the continuous time Fourier transform. So given a problem, given a signal, if you calculate its discrete time Fourier transform and you get something that is not periodic with period 2 pi as your answer, then you have the wrong answer. You've done something incorrectly. So stay tuned. We're going to look at some examples of how to calculate the discrete time Fourier transform, basically using those boxed equations. And we're going to see that our final answer is periodic with period 2 pi. All right, so I'll see you in the next videos.